My name is Antoine Delignat-Lavaud. I'm a researcher in Microsoft. I actually work for Mark Rosinovich. So technically, this is supposed to be a use case session, but I'm actually a researcher, so I'm going to try to sneak in some more technical and some research. And the topic of today is officially confidential inferencing. So it's how do we build confidential AI as a service. But what I want to actually say in this session is pick up on what Mark said in the keynote. So there is this idea that there are different levels of guarantees that you can get with confidential computing. So you can create some services that are just isolated from the infrastructure, that's kind of confidential. You have these services that guarantee that your data is always in a confidential computing boundary, and that's the in-confidential. And the most interesting for us in Microsoft is this kind of last class of strongest guarantee, these transparent confidential computing services, which mean that there are services that you can actually audit, and you can claim some properties that third parties can actually verify about your service. So I think during the Q&A and the panels, there were all kinds of questions about what are the blockers and what are the difficulties if you want to kind of build this this most interesting class of transparent confidential services. And that's what I want to talk about today, actually. And I'm going to use that use these problems to motivate the way that we have designed in Microsoft, the way we have designed our confidential inferencing service. So here we go. Why is it hard to build a fully transparent confidential service? So I think many people in the room probably have some experience. I have a lot of experience. I've been building confidential services for many years. So probably the top of the list is how do you deal with transporting the data from the owner of the data to the actual TE that is going to process the data. And that's kind of one aspect of it. The other aspect of it is how is a user going to verify the attestation, which is also typically the two are kind of related to each other, right? Because you want the way that almost all confidential services work is that you want to establish some attestation properties of encryption key, and then you are going to use that encryption key, which, okay, let's say public key maybe, because it could be also a signing key if it's a certificate that you use for TLS. And you use that attested key to establish a secure transport with the user. So that is one category. There is another category that is not actually very often mentioned in the sessions that I have seen in the summit, and that's how do you actually build scalable confidential services. So I think if you think about a service which is just one confidential VM, and then you have some users that connect, it's kind of easy, but it's not the way that real services work. What you want is you want to have scalability, you want to have many nodes in your inference service, many copies, possibly many different models running in your Kubernetes clusters, and depending on the loads, you want to reassign some nodes to serve a different model, so you want to scale it back. So that's the reality of things, and that's what we have to deal with. You also have this quite interesting problem that you have a ton of additional infrastructure around your confidential service. You have these front ends, which often are supposed to terminate TLS. You have these firewalls, application firewalls, load balancers, ingress controllers in your Kubernetes cluster. So all of this is part of your infrastructure, but obviously you don't really want any of these functions to have access to the secret data. Because why would they actually have access to this data? I mean, they are providing some useful functions, but they should not actually be part of the confidential trust boundary, as Mark calls it, of your service. So then there is this other aspect that is quite interesting and quite important of auditability and transparency. How are you going to actually be able to give this in-depth auditability guarantee about a service when you know that you're going to do service updates almost every day for whatever reasons, right? You have some OS updates, you need to install update on the operating system of the nodes, then you need to do some updates, right? And I think the general idea is that it's never going to be practical to expect users to be notified or review every update. It's just not practical. So the model that we always operate under is this auditability model. So we are always going to apply updates as soon as we can, but we are going to want to guarantee that all updates can be fully audited after the fact. And then I will also touch on the very last point, which is how do you deal with systems? And there were some good talks, actually, that touched on that problem. So when you start to introduce a confidential service that depends on another confidential service, then you start introducing these transitive trust relationships between services. And then it becomes very difficult to maintain this full level of auditability, because all of these services that are part of your system are going to be updated independently of each other. And obviously, the end user is only going to connect to the first TE. So even if you have direct attestation of that TE, all of the other TEs that it depends on for whatever function, database, maybe it's a vector database, if you're doing a RAG, whatever it is, then you lose kind of this level of precision and you need to recover some stronger auditability and transparency guarantees. Okay, so that was the motivation for this talk. Now let's talk about some of the designs that we have. I think this was also one of the things that was mentioned in the keynotes. What are some of the typical confidential service design patterns? And if you've been following the industry announcements, so Microsoft has announced confidential inference, Apple has announced private cloud compute, Meta has announced the WhatsApp thing. And if you look from far away, they actually kind of look the same. So all of them actually are using this protocol called Oblivious HTTP. And all of them have this component, which is the key management service that is going to actually be used to assist with the distribution of keys used to encrypt the prompt. It's going to assist with the distribution of keys to decrypt the prompts to the TEs that actually participate in the service. And I'll try to explain why. So the reason that we think that probably also Apple and Meta want to use Oblivious HTTP is because it operates at the application level, right? Which means that all of these untrusted functions that you typically have, the load balancers, the front ends, the firewalls, essentially these Oblivious HTTP requests are wrapped and they can pass through these layers without any change. And that's a very, very useful property. In fact, it's not what Oblivious HTTP has been originally designed. Originally, Oblivious HTTP was designed as a way of hiding the source of a request. So it was more designed as a privacy mechanism. But it turns out that it's also a very good mechanism to transport encrypted requests from a data owner to an actual TE. And then let you go through all of this middle infrastructure that you can keep untrusted. In the case of Azure OpenAI, we have a lot of infrastructure like that. Like we check the API keys for authorization of the request. The load balancing is very complex and goes through many layers. So we have to make sure that all of these functions, which are not critical to the confidentiality of the data, they remain untrusted. So next, there is this other property which is very interesting that unlike TLS, which is end-to-end, and it's fully ephemeral key exchange, Oblivious HTTP is only semi-static, which means that you have a fresh diffie-hellman share on the client for every request, but it's actually the same static share on the server, which means that you can distribute that share to many different TEs. And what that gives you is that it gives you the ability to do stateless load balancing. And for inference services, that's extremely useful, actually. Because if you want to do TLS connection between your clients and your inference TE, it kind of ruins your load balancing completely. Because then it's only that particular backend server that can answer requests from the clients, or you have to tear down and restart the TLS uncheck, and you have to reattest the full session. So that's why, actually, in a way, remotely attested TLS is actually really bad for building inference service, just for this reason that you lose the statelessness of load balancing. Another actually consequence of the fact that Oblivious HTTP is semi-static is that you can actually retry requests, right? Because the server share is static. So if you have one of the backend TEs crash or whatever reason is too busy, it cannot serve the request, that's okay. You can just take the request and you can give it to a different TE. And as long as it has access to the private key of Oblivious HTTP, it will also be able to decrypt the request and to answer the request. And maybe one last point is that it's actually quite easy to implement Oblivious HTTP clients, which is not the case of remotely attested TLS. So a typical example, I'm sure you've seen many demos of confidential inference clients, and the way that they show attestation in browser environment is that they are not actually doing remotely attested TLS in the browser environment, because this is extremely painful. You have to do WebSocket, and doing TLS from browser is extremely bad. So that's another aspect where actually Oblivious HTTP is quite good. You can very easily do HPK in JavaScript, you can do HTTP in JavaScript, and you can build clients. Okay, so the next aspect is managing these Oblivious HTTP private keys. So that's also a problem that many people have actually faced, and it's quite an interesting problem, because now we are also going to go into auditability aspects. So the way that the downside of OHTTP being static on the server is that you need to actually refresh the keys of the server quite often, right? As for any static key, the more you use it, the more it can be exposed. So you have to change that key quite frequently. And this ability of changing the key is actually dangerous for privacy. So you have to actually have only 8 bits identifiers for keys in Oblivious HTTP, just because 8 bits already lets you discriminate between 256 buckets of users, because the keys can be chosen by the server when you try to discover the public key that you're going to use. So that's where having this key management server that is going to refresh the Oblivious HTTP private key is important. So that is one of its roles, and the other role is also extremely important, is that it's the place that is going to control which TEs are going to be able to decrypt requests. And that's what we call the secure key release process. So you present an attestation, and you apply some key release policy, and if your attestation meets the key release policy, then you return the private key back to the TE. And typically it's wrapped under some wrapping protocol, but let's ignore that for now. And I think one of the interesting aspects that we also learned when you operate complex inference services is that secure key release policies have to be modular, which maybe is not something that is completely obvious to people that are outside of the big hyperscalers, but the reason for that is that there are different causes for attestation measurement change. So one type of change is that there's been some BIOS updates, vBIOS updates, or whatever firmware updates that needs to be patched. And then when you apply that patch, that will change some of the low-level measurements of your attestation, right? Because remember that all of the firmware is supposed to be measured in attestation. Then you also have a different class. Let's say you have in the operating system image, you have some package that needs to be updated. Well, that actually will change the image measurement of the attestation. And I think the most common one is, so we are going to deploy containers or workloads within this image. And so these container updates also will change the runtime attestation properties. So all of this actually, within large clouds, they would be performed by different teams. So the team that is doing BIOS updates is a completely different team from the team that is managing the Azure Linux image or the Ubuntu image that you use to run Kubernetes clusters. And it's going to be completely different teams that is actually programming the inference containers. So that's why for this particular project, we built our key management component on top of Azure Confidential Ledger, because it has this ability of having different user roles, and you can then program the application in the way that different teams can actually change the key release policy. And the other reason that we choose it is because it's based on CCF, so it has this verifiable ledger. So every operation, every change to the secure key release policy is recorded in the ledger and will be auditable. And it's kind of the first step in auditing the service. You need to understand, I use this public key to decrypt, to encrypt my requests, which keys have the ability to decrypt the request at any point. And if you want to answer that question, you have to look at the ledger and you have to look at the key release policy. Obviously, that's only the first step. So the next step, as I said, is that we are dealing with these complex Kubernetes deployments. So I think there's been a lot of progress in Coco and Kata containers. So now I think there is kind of good understanding of how do we actually control the deployment of containers within TEs. But still, if you want to go further, what you want to do is you want to guarantee the auditability of deployments of containers in a dynamic environment, which becomes kind of the next level of complication when you want to look at this problem. And that's where you need to introduce kind of these new mechanisms to control that every deployment that you receive from the control plane, so you have a Kubernetes control plane which you don't want to trust. Is going to be essentially operated by Microsoft employees for a Microsoft inference service or whatever infrastructure provider. So you don't want to trust the Kubernetes control plane. What you want is you want to trust the ability to audit every deployment that have been received from that control plane. And you also, as an Azure property, which is more commonly understood, you want to ensure the integrity of every container that have been loaded into this environment. So the next point is using the cloud transparency service. So there have been several presentations already about this. So I'm not going to go into many details. So we have built this new audit infrastructure in Azure. We have the cloud transparency service. And we are developing this new approach for having confidential build pipelines that are going to sign artifacts which are made transparent on the CTS ledger. And that's exactly what you want when you want to build an inference service. So you're going to have the build pipeline when you want to build your inference containers, and it's going to sign these containers and make them transparent. And at the same time, you also have these deployments, which is essentially the pods configuration that are going to be sent by your Kubernetes control plane to be deployed in your cluster. And you also want to to sign them and make them transparent to kind of get the full auditability story of the service. So let's also talk quickly about rolling out code updates. So as I was saying, in real production systems, there are updates to these services almost every day. So what is going to be the process? So we want to have a process where we can update these services in a way that they remain fully auditable, but also that you can do a rollout which does not impact the availability of the service. So if we follow the flow, you first start a confidential build that is going to produce a new containers that is going to be signed, and you will have a transparency receipt. And you're going to push this container to your registry. And then you have to create a new deployment, so which you also have to make transparent. You will use your transparent signing service to sign your deployment. And then the next step is that you create a new Oblivious HTTP key. And you're going to assign to it a key release policy that is going to authorize both the old deployments as well as the new deployments. So that's kind of important to make sure that during the rollout periods, both the old and the new deployments will be able to do key release if they receive a request encrypted with that key identifier. So then you wait for that key, the previous key to expire, and you can start scaling up and down the old and new deployments so that depending on your spare capacity, you can do it one node at a time, you can do it at different pace. But you replace all deployments by new deployments in your cluster until the point where all of the nodes have been updated to run the latest And then at that point, you can create a new Oblivious HTTP key, and then you can deprecate the old key release policy, and then from that point on, all requests will be using the latest deployment key release policy. Okay, so that's a high-level view of how we actually designed the Azure confidential inferencing. What I've noticed in this summit is that there have been very, very few demos, which is quite disappointing. So I've decided to be a bit bold, and I try to see if I can do a live demo of confidential inferencing. And to make it a little bit more interesting, so remember that what we have made public so far has only been for speech-to-text. So it has been for speech-to-text because of essentially reasons that relate to responsible AI. But we still have the ability, thanks to NVIDIA, to run multi-GPU. So we have access to H200 GPU systems, and we actually can run large models. We can run DeepSeek R1, and as a demo, what we built is one of the most popular extensions. Let's see if I can switch. Yeah. So I'm sure many of you have used this AI agent in Visual Studio or in different tools. And they are probably the most popular application and the biggest market for AI today. So it's kind of a natural way to see, can we provide a confidential version of this experience because it's such a popular experience. So what we did is we took one of the most popular extensions for this, in this case, this C-line, which comes from Anthropic, actually. And what I did is that I added inference provider, which includes this Oblivious HTTP client so that it can request, it can do confidential inference requests to Azure Confidential Inference Server. So let me see if I can. Yeah. So as you can see, I defined a new inference provider which use this endpoint and the key management address, which is where we're going to fetch the Oblivious HTTP public key. And that's what we're going to use then to, as if it was a normal OpenAI endpoint, more or less. And we can actually run. So in this case, I had some sample prompts where I actually asked the model to program a library in Rust that can verify attestation reports from TDX and from SCV-SNP. And then I'm sure you've tried this kind of things. So it uses DeepSeek. So this is a reasoning model. So the way this works is that is going to generate these reasoning tokens where the model is thinking, okay, here's the task that I've received. I'm going to actually do that. So all of this is done live. So there is kind of quite a risk that I'm at the mercy of the network, and the network of the conference has not been so great. So hopefully we do get some answer. Anyway, so I'll put it back on my screen, see if it takes some time. And maybe in the meantime, I will just quickly finish about a last point that I wanted to bring. Actually, I may run out of time. So the last problem that I mentioned in the list at the beginning is we have these two. So we have this problem that some TEs, they want to communicate with dependencies in the background. And what is the most efficient way that we can enable this server-to-server communication? For instance, if you have inference and you have a vector database, how do you create these secure channels? And we have published this new paper, which is going to be presented at Usenix in August, which actually talks about how we distribute attestation materials through DNS, and how do we make the DNS infrastructure transparent so that you can audit the full system through the DNS. So if you're interested into that, we have the paper on archive, and I'm also happy to discuss it with you after the talk. Okay, so unfortunately I ran out of time, sorry, but I still hope that it was an interesting presentation for you. We have our open source confidential inference clients, and if you want to try it, as I said, Whisper is available. I can give you some free API keys if you want to do some free speech to text. And I welcome any question. Thank you.